Sir, 5 minutes, sir.
Ah,
Uh, a very good morning to one and all. Once again, we have just come for another lecture, which is for the Atal Faculty Development Program, sponsored Atal Faculty Development Program, organized by Bundelkhand Institute of Engineering and Technology, Jhansi, Uttar Pradesh. So today, as our speaker, we have Professor Santosh Kumar sir from the Department of Mechanical Engineering, IIT BHU, Indian Institute of Technology BHU. He graduated in production engineering from NIT Allahabad in 1986. He did his ME in 1988 from NIT Allahabad itself, and he did his PhD work from IIT Kanpur way back in 1999 under Professor G.K. Lal and Professor Kripashankar. He is having work experience in industry as well in Ispat Industries, Mumbai. So Professor Kumar sir bears a very good academic record, and he has published more than 70 international and national journal papers. Professor Santosh Kumar sir has guided about 28 UG, 32 PG, and 35 master's theses to his credit, and he has published 14 articles and has developed courses related to technology of competitive manufacturing and metal forming. He has conducted several short-term courses for teachers at national level, and he has also organized conferences including 22nd National Jeevan Vidya Sammelan 2017. And he is also the chairman of the induction program outreach cell IIT BHU. And he has completed 8 sponsored research projects, and currently there are 4 projects which are undergoing under his supervision. And he has also worked as a consultant to many industries for industrial problems. He has developed 4 new machines from scratch for government organizations, 3 of them which are patented, and he has very extensive academic administrative experience at institute level and at the national level also. And he is well established in the area of automation and manufacturing, and and also additive manufacturing. He is also has been in charge of CAD/CAM and production laboratory at IIT BHU Varanasi, and enjoys institute administrative jobs and activities as well. And he has developed additive manufacturing lab, including incremental sheet hydroforming lab in production engineering department. Welcome you, Professor Santosh Kumar sir, for our Atal FDP program. Thank you so much for accepting our invitation. We welcome you to take a lecture for our FDP program. Thank you, sir, for coming. Sir, over to you, sir.
oh, thank you. So, thank you very much for uh, giving me this opportunity. Uh, this Atal AICT funded project, FDP. So, the the topic that have been given to me is uh, micro manufacturing using additive manufacturing or 3D printing. So you understand the word additive manufacturing, all of you might be knowing. Have you heard this term? How many of you have heard this term? Hello?
Hello. Yes, sir.
So how many of you have heard this term? Additive manufacturing? Huh?
Yeah, good morning, sir. So that is a very common type of manufacturing process what we are using right now as a layer process, or we are using 3D printers similarly for the manufacturing of some components.
Yeah. So you know the additive manufacturing, and now there's this name is, earlier it was named as rapid prototyping, and then today it is known as additive manufacturing in academia, and in industry it is known as 3D printing, you know. So, and it is also known for other name. It is very popularly, and why it has become so important, that it's a manufacturing in a natural way. Hmm? So see, the additive manufacturing, it is a different technology that has developed in last after 1980s around. It is now it is called as a disruptive technology now, because it's a natural way of developing products, natural way of shaping. Bigger object has been done, but this talk is concerned with the micro level. So at micro and micro level, the additive manufacturing process, if it is correctly approached, it can lead to the fewer design iterations, less assembly work as a result of part consolidation, as well as inventory reduction. And after all, if little or even no assembly is required, there is also no need to carry an inventory of different components, nor for a stock of fasteners such as screws, bolts, etc., or any other thing. So that is what I'm trying to start with. But before understanding, going into the deeper part of the micro manufacturing, let us understand the history part of it. So the additive manufacturing, if you look at the timeline here, it is started named as rapid prototyping 1988-94. Then there has been addition of different processes using additive or rapid prototyping, like rapid casting, rapid tooling, additive manufacturing for automation, automotive in 2001. Then in 2004, you can see that uh, uh, it became other part, like uh, medical applications, aerospace application, eh? And you will see by 2013 to 16, nano manufacturing. So nano manufacturing is much smaller than the micro level we are going to talk. Then there is the bio implants, in situ manufacturing, full body organ. So all these things are ahead, but we will limit ourselves to. So now this screen you are able to see. Huh? Hello? You are able to see this screen, please?
Yes, sir. Yes, sir.
So let us see quickly these items, that is the history, technology, because otherwise you will not get connected. So as I said, the rapid prototyping or additive manufacturing or 3D printing it is a digital manufacturing. It is called as a digital manufacturing that uses a CAD tools to create it, and then transfer it to the CNC machine, which is called as additive manufacturing machines, and then it will print. You know the 2D planar part printing, you are all aware of. Your 2D printer, paper printer, that prints on 2D color 2D printer, laser color 2D printer. Eh? And you will also come to know other technologies like 2D part, planar parts, laser cutting, water jet, complex shapes, 3D printing, like that. Hmm? So these are your non-rapid technologies. So what happens in non-rapid technologies? It requires no skill. It is potential for injury. That is the conventional. Potential for tool damage, and may entail lengthy preparation of high setup costs, offer a wide range of materials, and it can be optimized for mass production also. That is what is non-rapid or conventional way of manufacturing, right? So let us see what is the 10 principles of 3D printing or additive manufacturing. This is very important. So this principle is valid for bigger 3D printing as well as miniature or micro level 3D printing or nano level 3D printing. Okay, so these 10 principles do not change. Let us see. So it was first proposed by Lippmann and Comran in 2013. That's how it is written here. So number one is that manufacturing complexity is free. As compared to the conventional, here you do not require any extra cost for uh, 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 for other shape, for complex shape. For suppose there is some extra holes, extra features, then you do not require any extra cost. Whereas in other conventional way, you require extra cost. Variety is free, so no cost to make many version of the item. Yeah,
Excuse me, sir. Sorry to
yeah.
interrupt. Sir, can we
Uh,
have the full screen of the presentation if you don't mind?
Full screen. Yeah,
Sir,
I think
slideshow.
now it is.
Yes, sir. Yes, sir. Thank you, sir.
Now it is okay.
Yes, sir. Yes, sir.
So variety is free, and then no assembly is required here. That means the whole assembly you can print in one go. There is nothing like print and assemble. You can print interlocks part or multiple materials at the same time. Like you have a door plus its hinge, you can print simultaneously. The fourth principle is zero lead time. Zero lead time, that means you can print on demand, no waiting for the parts. You get the CAD model and immediately print. Fifth is unlimited design space. So that do not require and is subject to the geometric constants that limit the, like geometric constants are there on the conventional machines like lathe, milling, molding and all that. Here there is no geometric constant. You can print the object as per the table size of the printer, and even if it is bigger, you can cut in pieces and then print on the same table, and then later you can assemble or join. Then six is zero skill because it's a CNC machine based printing. So if and the programming is also automatic here because the software is of the printer is such that you have to just put the CAD model or the STL file of it, and then automatically it will do everything, slice generation and all that, and it will print. So nothing you have to add from your side. So that is, you do not require any skill therefore. Seventh principle is that it is compact, portable manufacturing. So the printers are very small, and it requires very small built space to print a large component also. Eight is that less waste by weightage because there is no chip formation like in milling and machining operation. So you require almost negligible waste material here because it works on layer wise deposition method. Ninth is infinite sets of the material. So you can blend material to produce continuous variations in hardness, color, and etc. That is possible here. And last principle is that the precise physical replication. So very high resolution scanning in the digital design files can allow exchange of the 3D objects in the 3D data, and you can then make the CAD model from the cloud data, and then you can print exactly the same. So these are the very, very fundamental principles of 3D printing. So why I am saying it is a natural process, because if you look at the cocoons, spider, mud bees, etc. in nature, and also the making of jalebi as a sweet. So based on this inspiration from the nature, in 84, people thought to make a machine. And because there was a lot of development of CNC machine, so it was easy to conceive this idea. And in 2005, Dr. Adrian Bauer, he developed such a self-replicating 3D printer, and later uh, it has a public license then later. And then nowadays you will see a lot of printers are available. So now you see, this is what is the inspiration from nature. So can you notice what it is? Anybody? Can anybody answer what it is? Hello? Hello?
It's a cocoon, sir.
What it is?
It's a cocoon.
Exactly, cocoon worm. So this cocoon worm that eats a leaf, very popular leaf, and through its salvia, uh, uh, it it makes a thread-like structure. That is what you call as a resham, na? And because it makes to his shelter, because inside this worm lives inside as a, and later the human learn to use this for their business, because they learn how to kill this worm and take out this deposited thread like structure, right? So this is what is in nature already. You can also see these things in most of the rainy days. You can see these structures. eh? Hello, you might have seen these structures. Is it, am I right?
Yes, sir.
Generally this is a mud and a mixture of, say, small tiny grass, dried grass, mixed with, say, uh, these insects they create for their shelter. Again, for shelter, are laying their eggs inside for safe conversion from the pupa to the grown one. These also you can see. The honeybee also, there is a lot of things. So they are the carriers of 3D printers. You know? Now you see this one is very natural. You can see even today. And then based on that, because in 18th century mechanization started, and then the computers developed and all that, and 20th century mass production, and so you can understand the additive manufacturing is a next industrial revolution which talks about the additive way of making, and earlier conventional method has been subtractive way. So, so it has a lot of applications. It has applications like uh, many applications. So this is the subtractive way, right? So this is the difference, additive and subtractive. In additive, you create a form. In subtractive, you uncover a form. In additive, there is a conserve of resources. Here you have carving, sculpture, like that. Additive is efficient, uh, and but subtractive is wasteful, time consuming, like that. So these are the basic steps in additive manufacturing or rapid prototyping. You can see this is the basic step. I said it is also called as a digital manufacturing. So you start with a CAD model. You can choose any software to create CAD model. You can create using surface modeling technique or like that. And then that CAD model is converted into stereolithography format, .stl. So the .stl becomes the input for the pre-processing. From the .stl file, uh, the required support is generated, and then slicing is done, and then this sliced data is sent to the 3D printer or additive manufacturing printers, and it will print layer wise. So that is what is called as the both processes. Once it is printed, you have to remove from the platform. You remove the support material supports if it is there, then you clean the surface, and then little bit post curing is required, and then you get the part. So this is what is the fundamental process of any additive manufacturing process, whether it is a metal printing or plastic printing or any material printing, composite printing. eh? Either it is in color form or black and white or whatever it is. So that's the very fundamental you might be knowing. So this is one of the metal printed part. eh? So you see that the additive manufacturing has a great development at the level of material development, process development, software development, design, and even today production. So mass manufacturing is also going to become very soon with additive manufacturing. It has a great advantage. All over world, it is becoming very popular, and you can understand that it is becoming a very huge business in coming period because of its advantages like design complexity, speed of printing, customization, tool less printing, and all that, and sustainable. It is sustainable to the environment. There is no storage cost, and also it leads to increased employment opportunities. Disadvantage is that the accuracy is not as compared to the conventional way, and the support material removal is a one problem here. Limitation of the raw material is there, and considerable efforts it requires for the applications design and for setting up process parameter. Material cost is also, for metal it is costlier, and material properties, uh, not many material properties are available. So that these are some of the disadvantages, but in time to come all these things will get over. So another thing is that intellectual property issues are there, limitations of size is there, but this size is no more limitation now. You can print very bigger. Now the whole 3D printed houses are also printed. So that has already spread. So in 24 hours, you can print, say, 4-story building, a total flat system. So that is now coming up one by one. So that is, you can see that the it requires planning, design, like that. So these are other applications. What I was talking about. So you have this way of, as I told. Uh, so these are the different. While printing, you have different processes and issues related with the additive manufacturing. This is what I'm putting it again in a different way. So these are the some conventional. So see, this is a support material. Here it is a support material. This is also a support material, which is required for printing. Otherwise, it will not get printed. Like here. So these are the holes. Like so here, see, this is the support material. This is support material, and these are also support material. So the process has a different process. Additive manufacturing, liquid base, powder base, and solid base. In liquid base, you have stereolithography, jetting system, and direct light processing system. That is DLP. Powder base, you have a lot of like SLS, three-dimensional printing, fuse metal deposition systems, electron beam melting system, selective laser melting system, selective masking sintering system, selective inhibition sintering, electrophotographic layered system, manufacturing, high-speed sintering system, and solid base printing has the fuse deposition modeling and the seat stacking, that is called as LOM system. So these are the some of the technologies. Stereolithography is a liquid base where the photo resins are used, and with the application of laser it will get cured, and layer wise there it is cured one above and printed. There is a DLP, it is similar to that. This is what is the laser melting process where you use powder based. So there is a fuse deposition modeling where you have a heated nozzle and the filament melts there, and then it gets deposited layer wise. So fuse deposition is very cheaper way of printing. And this is the LOM I said. Here the a sheet is laser cut and it is deposited one above. So every layer is laser cut from the sheet and it is deposited one by one. And the cut reeled, it is wound on the other side. So that is what is the, this is a laser. It cuts the layer. Binder jetting is another technology where it is inkjet printing line. So binder jetting is like just like a 3D printing, color printing. So here you can print. This is a voxel jet. So voxel jet is a 3D direct 3D printing. It prints in 3 dimensions, whereas the conventional the additive is layer wise 2-dimensional printing one above. But here it voxel is a 3D area printing. You can have you can make lot of toolings, and so these are some of the material powder, metal powders. You have metal powders, you can mix, you can form a alloy and you can metal printing. So this is one of the ornament printing, that is the SLA printer. So these are the some SLA printers. So this is a binder jetting. So a lot of material you can print. You can print nylon, ABS, PLA as the plastic material. Wood material, the wood, plastic, and also stainless steel, metal printing, titanium printing, ceramic printing, paper, biomaterial printing. Skin can be printed, food item can be printed. So lot of things you can print. Now I come to the important part of that miniature part, the micro. Generally, micro label printing, you can use FDM, you can use SLA, and you can use electron beam printing. See, most of these printer has presently, which is low cost printer, which is available in market. It is about 100 microns, 100 micron accuracy you can print. So you know that any feature, if it is 100 micron, it is already a micro label. So you can print at least 100 micron. So that's a good, very good. The SLA printer, like most of the SLA printer, it goes up to 50 micron, sometimes 20 micron also. So 20 micron printer like Formlab 3, Formlab 2 that we have in lab. But Formlab 3, it can print up to 20 micron. So very small miniature features you can print. So the question is that how do you use this technology for the printing? So that's what I say, that the 3D printing is now it is already established. Now your job is that how do you exploit this technology? How do you exploit in the sense for the micro parts? So micro parts, whatever you print, it should have a good quality, good strength, and the dimensionally it should also be very accurate in micro dimensions. So generally the challenge is, if you look at the micro level, we have the challenges are at the process level, at the material level, at the sub-size level, that is the micro and micro, and the application area. So the 3D printing, when you use laser-based technologies, that is what is suitable for more suitable for micro level and micro level. You can use 3D direct writing. You can also use a hybrid printing, as these are the processes. Material based, you can print nano particle size. You can mix with these photoresins, nanoparticles, and then you can print. The liquid metal resin based can be used for printing. Filament based printing can be done. Reactive metals like titanium, magnesium can be printed. And the reactive metal inks are there. So you use metal inks, and then powder based micro nano size powders are used for using SLS process. And size, you can, no doubt, you can print micro nano. Now people are talking about nano size printing. So generally applications of micro nano is that most of the sensors you see that is being printed, electrochemical applications, and microfluidics is the very important area which is now coming up. So now let us see some of the component which is of very small size. You can look at here, right? Like you see this one, it is of almost less than 1 micron, 1 mm, less than 1 mm size, and see so many features. Now here if you see tip of the stick, now you see this is this is a metal uh, the, electron beam printed component. The size you can compare with the stick generally used in house. Now this is another class of very small. See, these are the small SLA printed components, your rings, finger rings. Here also it is finger ring. This is the metal printed one. You can spring miniature springs and miniature other parts. This is metal. You see the size, it is coming on the palm, and it is very complex features. Now this is another one. This is of nano size. These nano springs. You can see this is the nano. All these nano size. It is 30 around 10 micron. So this is the 10 micron. This is 1 micron. This is 1 micron hole. And you just see this is a very miniature metal printed component. This is one of the laboratory for the micro and nano printing lab. This is one of the printed part, plastic, that is SLA printed component. And this is another one. So this is this is a microfluidics. It is a very nano size thin channel you can print, where so here you see this is a one SNEC, which is MRI. It is MRI and then printed. After the MRI, you can develop the CAD model, and then you can print. MRI X-ray data can also be converted into CAD model. So these are SLA printed. And this one you can see, this is and this is the, see, this is one assembly printed. You can see it's a fly. This is a gear which is, you can see the 0.13 mm, and this is the feature is around 0.092 mm. So this is a small feature, and you can understand. This is one of the motor geared motor, which is generally used in 3D printing pens. This is very popular motor, and it is available within, I think, 300 rupees. It is just like equal to your thickness of your finger, and the gears are so small. It runs around say 50 RPM. You can see here. So this is also another microfluidics application. This is another motor, whole motor. It is miniaturized one. This is a micro extrusion printing, generally used in biomaterials. So biomaterials, like you can print skin, you can print bones, you can print body organs later. So that is what is the applications of all micro levels. This is one of the drone, which is a micro drone. This is another an assembly for running with belt and all that. It is of micro level. It is just like on top. There is another one, nano size printing. You can see this is the printing where there are gears printed, and the comparison is made is with the pencil tip. This is another one. This is the whole engine printed at very small level. You can see it is a SLA printed here. This is another aircraft, full aircraft, color aircraft printed. You can see this micro 3D printing on the finger. Such a small, it is all metal printed. These metal printed has the same object in 3 different sides. You can see. This is one of the fly. The fly size is compared that you can print. This Tico is one printer which is very popular for micro 3D printing objects. Tico is specially designed, very palm top printer it is. These two are other printers. This is the bio printer, very small bio printer. This here also. See, very bio printer, you can put it on your just palm. So that is what is going on today. The bio printing is, it has become very popular. The only thing is that 10 principles is here useful, and it is the parameter you decide on the printing. So generally for micro printing, you have to use so that is what is you can think of. So the micro printing, 3D printing has gone quite beyond. At the cell level, now the cell is also being printed. So every area, not only the metal, plastic, the polymers, the bones, biomaterial. So all these things are happening very rapidly all over the world. So the area is very bright, and in India also people are working. So I think I will stop it here, and you have any question, I am available. Okay. All right. Any question?
Participant, do you have any questions? Hello. Please feel free to ask some questions. Yes, Shivali ma'am.
Yes.
Any question? Hello.
हाँ, बोलिए अरुण जी. Any question? So you could understand or not? Hello, Abhishek Trivedi. Huh?
Uh,
Yes.
You can write it in the chat box. Otherwise, I'll just read it out if you have any question in mind or any
Yeah.
research that you're going to do in this area.
So the area of micro additive manufacturing is very bright. Very few people are working in India.
Hello.
Yes, tell me.
Sir, what is the scope of research in this field, sir? If you just see
Very high
down the
scope.
lane, like say 20 years down the lane, sir.
Very high scope. This is the area that is going to evolve in coming future. Every area. Medical science is going to grow very fast because the biomaterials, bioprinting is becoming, and very soon the body organs printing is already there. It will be available commercial with body organs, 3D printed body organs.
But sir, the machines are quite costly, sir. Uh,
It is
Sir, how
costly
do we
because
compensate,
users
sir,
are
for
very
that?
less. Because users are very less. Anything is costlier. It depends on the uh, users. If there are more users, more demand, then it will automatically become cheaper.
Yes, sir.
Okay.
Yes, sir. Thank you, sir. Any more questions from the participant side? If not, we can just. Sir, Professor Santosh Kumar, sir, thank you so much for joining us today and giving your valuable time, sir.
Thank you.
Thank
Thank
you,
you
sir.
all. All the best.
Thank you, sir. We'll be we'll be having the next session after post lunch. We'll be having the next session around 2:30. We'll be having the next session. Thank you all for joining.
Thank you, sir.
Thank you, sir.